ก็อันนี้เป็น2 สัปดาห์สุดท้ายของวิชา Catalyst Stability นะครับก็คือความเสถียรของตัวเร่งปฏิกิริยานะจะเป็นการพรีเซนต์จากพวกเราเนี่ยนะครับจากหัวข้อที่เราไปหามาก็เดี๋ยวจะอธิบายนะครับ Lecture วันพฤหัสที่22 เมษายน 64ครับโอเคthis is the last lecture for the last 2 weeks of the Catalyst Stability to 105633 on the 22nd of April 2021 and we will start at 8:45 we will start with the student scan and 2 referees please be prepared student number 2 and 3 okay so for the score it will be in 2 parts the presentation and the report so the 15% came from my evaluations 5% and 2 referees of 5 each and the report is also 15% so it will sum up to 30% and this is the schedule for today so we also have the moderator to control the presentation time is the moderator here so we have Atachai and also Jantip and who else the last one
Supavit
Supavit Bunchui okay not here yet so we have 4 more minutes Scan please share your screen okay please test the microphone and what the referee will do is that they will ask the questions if actually they will write a question within the evaluation sheet and then because we only have 8 minutes so if I don't think we have time for questions so let's just mark the questions within the evaluation sheet so our referees 2 and 1 and 2 here Kunanon and Jagapan
ฮัลโหลเทสได้ยินไหมครับ
ได้ยินครับ okay we have 3 more minutes and the moderator will notify you when it's 3 minutes left so at the minute 4 they will tell you okay please use the laser on the screen please Scan, please change the cursor to laser. Control L. Okay. So we have one more minute. I think we'll go now. Okay. Please welcome Scan, uh,
Good.
PhD candidates. Okay.
Just begin. Okay.
Okay. Please start.
Good morning.
Moderator. Prepare.
Okay. Good morning to Ajahn P and everyone. My name is Sakan Pidavijit M. First presentation. Today, I would like to talk about the topic of the factor of coke formation in copper-based catalyst. Begin on the outline. I separate in three parts. First, literature review. Second is summary. In the last one, recommendation for the future works. In In 2003, Twing and Spencer studied the activation of copper metal catalysts on methanol steam reforming and methanol synthesis. Copper catalyst has a very low activity for breaking CO bond or for forming CC bond, and as a result, wax formation of coke from any hydrocarbon that may be present. Nevertheless, although coke formation is essentially unknown in metal synthesis, it has been observed in the reverse reaction methanol steam reforming. The origin of this unexpected carbon formation has not been established, but there are several possible causes. Carbon monoxide disproportionation reaction in the orange equation may occur if the reaction is thermodynamically favored. This equation is can predict to the carbon formation for uh, hydrocarbon reforming. Simon et al. 2012 focused on the deactivation of copper-based catalyst for the dehydrogenation of cyclohexanol to cyclohexanone. XRD analysis evidenced the presence of coke deposited at a high time on steam, while the simultaneous decrease of the relative copper concentration and the increase of carbon concentration suggest that copper deposition takes place preferentially over the copper active sites. The XID was shown in this figure. The carbon content increased with time on steam about 7.67% weight. Uh, Course on C1 has deposited at 395 hours, while about 5.64% weight coke on C2 catalyst has been observed at 349 hours. The ratio, the ratio between intensity of the peak associated to the copper crystalline at the intensity of the characteristic peaks of carbonaceous species also decreased during the reaction, probably as a result of the coke deposition. You can see the crystalline size of metallic copper increased to a great extent with the time on steam. Zhang et al. 2020 investigated on highly efficient, robust, and stability of copper silicon dioxide catalyst for non-oxidative dehydrogenation of ethanol prepared by ammonia evaporation method. This works out to 0.025 and 0.015 gram of CSX per copper gram per millimole. This shows the amount of coke. For 500 hours uses 10 and 20% percent weight of copper silicon dioxide AE respectively. In the comparison, much higher value were found for this one, 0.5 to 2.5% weight of copper silicon dioxide after only a few hours on steam. Thus, it can be concluded that the coke formation is especially pronounced as low metal loading. The main cause of catalyst deactivation was found to be coke formation. The coke to copper ratio in use catalyst varies inversely with
2 minutes
the
left.
loading. This slide shows coke formation is especially pronounced as a low metal oxide loading. Uh, this this slide shows the summary. First, cold dispersion and accumulation over the copper catalyst external surface play a major role in reaction deactivation as contribute a great portion to the total coke amount. The second is the reaction time and temperature influence the coke formation on the copper-based catalyst. The third is hydrocarbon reaction can have side reaction leading to the formation of coke. Uh, the last one is show different amounts of copper has different activity and catalyst with high activity has high rates of coke formation. This slide shows the recommendation for the future works. First, uh, focus on reducing the size reaction that can cause coke formation. Second is study the coke formation mechanism on copper-based catalyst. Third is coke formation can be minimized by selecting an optimized catalyst property improvement. And the last one, investigated improvement the property of copper-based catalyst to produce the lead coke. Thank you for your attention. You have any question?
Okay, thank you, Sakan. Kunanon and Jagapan, have you already summarized? I mean, have you already evaluated his presentation? Please turn on the mic. Hello.
ครับ
Are you done?
โอเค
Okay, อะไรล่ะอังกฤษสิ
เสร็จ
วะ
แล้วครับอาจารย์
Okay. Okay, so thank you, Sakan, our PhD candidate. Okay. Next, Kunanon, please share your screen. Sakan, please stop share the screen. Please stop the share screen. Okay, thank you. Okay, you have 15 seconds to start.
ขึ้นไหมครับ
Okay, I see. Speak English. There's no Thai here.
Let's begin.
Okay, now let's go.
Okay. Good morning, everyone. My name is Kunanondit Saphonjale. Today, I would like to present the topic of sintering of nickel catalyst supported on gamma alumina in carbon monoxide methanation. My presentation will be in three parts: introduction, literature review, and research direction. Firstly, the introduction. This is the reaction pathway for the carbon monoxide or CO methanation reaction. CO and hydrogen are feed, methane is a product, and water is byproduct. Secondly, the literature review. The first paper is anti-sintering zirconium oxide modified nickel catalyst supported on alpha alumina for CO methanation, published in 2016. Experimental, the obtained nickel oxide on alpha alumina catalyst what denoted as 10 Na with a nickel oxide loading of 10 weight%. Zirconium oxide modified nickel oxide on alpha alumina catalyst was prepared by the modified impregnation method. After the above procedure following this figure, the obtained samples were denoted as 10Na as zirconium oxide -X, where X represents the 5, 10, and 15 cycle time. Discussion: Effect of zirconium oxide additive amount. The CO methanation reaction was carried out in the following condition, and the results are shown in the figure A to C. It can be seen that the addition of zirconium oxide considerably improved the catalytic activity, and 10Na that loads zirconium oxide 5 cycle show the best catalytic performance and methane yield. It could be pointed out that the order of methane selectivity of the different catalysts is opposite with their order of CO conversion, indicating the side reaction can also be significantly enhanced in the presence of the more active catalyst. So only the proper amount of zirconium oxide can remarkably enhance the CO methanation, and the excess zirconium oxide had the adverse effect on it due to the coverage of the active site. Catalyst stability, effect of adding and non-adding zirconium oxide additive. In order to evaluate the lifetime of the catalyst, a 103-hour lifetime test of 10Na and 10Na that loads zirconium oxide 5 cycle was carried out at high temperature and also evaluated at a comparison in the figure. During the test, the CO conversion and methane yield over 10Na that loads zirconium oxide 5 cycle decreased less than 10Na catalyst, so it exhibits a better stability, especially at high temperature and WHSV. Conclusion: in a 103-hour lifetime test conducted under present condition, 10Na that loads zirconium oxide 5 cycle display a high stability and resistance to nickel sintering. Characterization indicate that in the preparation process, zirconium oxide particles are formed and interspersed among the nickel particles to restrain the growth of the nickel particle during the reduction and catalytic reaction at high temperature, resulting in the high stability in the lifetime test. The second paper is deactivating of nickel on gamma alumina catalyst in CO methanation effect of zirconium magnesium barium calcium oxide promoter, published in 2017. The objective is to evaluate the effect of different structural promoters on thermosintering under relevant methanation conditions. The resulting catalysts containing 30 weight% nickel were named according to the promoter used. This is condition that accelerate aging test thermosintering study. As can be seen, all the catalysts deactivate after the aging treatment. Indeed, the loss of activity is almost complete after aging at 30 bar. Moreover, as can be deducted from the figure, the loss of activity is explained by a loss of nickel surface area. It may be noted that under this operating condition, all the promoter present a positive effect on the initial catalyst activity. Conclusion: the catalyst lost particularly all their activity after the aging treatment. The loss of activity was explained by a loss of nickel surface area.
2 minutes left.
The loss of metal surface area was ascribed to sintering of the nickel particle and pond collapse. The use of zirconium oxide pre-stabilized alumina carrier with wider pond is recommended for clarifying the These possible effects of this promoter and also to avoid sintering of support and encapsulation of nickel particle. Finally, the research direction to solve sintering. I suggest that firstly, increase the surface area and pore size of support and use various support that provide strong metal support interaction. Secondly, the use of sodium oxide on pre-stabilized alumina carrier to avoid sintering of the support and encapsulation of nickel particle. Finally, various approaches have been employed to stabilize metal particles. For example, by adding inorganic oxide where chemical vendor deposition, atomic layer deposition, encapsulating with D-dimer, graphing or formation of the well-defined cavity or channel such as core shell and other mesoporous structure. Thank you for your attention.
Okay, thank you, Kunanon. We have 1 minute left. Jagapan, please prepare. Okay, 30 seconds. Referee 3 and 4, please evaluate. Okay, 10 seconds. Okay, we start now.
Hi everyone, my name is Jagapan Sangin, and today I'm going to present about catalyst deactivation in the topic of carbon formation on nickel-based catalyst in steam reforming process. And this is my outline of my presentation is about introduction, literature review, and research direction. Let's start with the introduction. What is carbon formation? It is the deposition of carbon species from the fluid phase onto the catalyst surface, and this process results in loss of catalyst activity. And nickel-based catalysts are commonly used for steam reforming because of their high activity and lower cost in comparison with precious metal-based catalysts. And what is steam methane reforming? It is the process which methane react with steam or water under 3 to 25 bar in the presence of a catalyst to produce the synthesis gas. And this slide is talk about steam reforming process. It is the conventional method to produce synthesis gas from natural gas or methane and utilized on the industrial scale. The reaction that occurs in this process is shown in reaction below. Methane react with water in the vapor phase to produce CO and 3 hydrogen gas, and this reaction is highly endothermic. It needs heat about 206 kilojoule per mole to succeed the reaction. And this is a process overview of steam reforming process. This is a diagram of steam reforming. It starts with feeding methane into the sulfurization unit to remove sulfur impurity in methane, and then react with steam which come from the heat recovery and add fuel to generate heat for the reaction. The reaction takes place in reformer at about 850 to 900 degrees Celsius, and then go to shift conversion and pressure swing absorption to separate hydrogen gas and carbon dioxide. Moving to the nickel-based catalyst in steam reforming, nickel-based catalysts such as nickel on silica alumina or nickel on alumina are commonly used for steam reforming because of their high activity at low cost. Due to alumina acid site, this catalyst tends to favor carbon deposition, so nickel catalysts are mainly deactivation from the deposition of carbon, even when operating at steam to carbon ratio, which is outside of the carbon forming regime. Carbon deposition on the catalyst surface causes the catalyst deactivation, and there are two principal carbon deposition pathways for steam reforming of methane. First, the methane decomposition, which is shown in Reaction 1. Methane decomposed into carbon atom and hydrogen gas. And the second is CO disproportion, which is CO disproportion into carbon and carbon dioxide. And two carbon atom risk cause carbon deposition on catalyst surface. The tendency to carbon deposition depends on the atomic ratio of oxygen to carbon and ratio of hydrogen to carbon. Lower water to methane ratio and hydrogen to carbon monoxide ratio, leading to higher tendency toward coke formation. And coke formation is relatively serious over the catalyst used for reforming at high temperatures. For the effect of firing by carbons on the catalyst, the carbon can diffuse through and begin to grow filaments from the backside of the nickel particles, especially at high temperature and low steam to methane ratios. The nickel particles are pushed off the support surface. Thermal or mechanical shock can cause the carbon filament to fall off the support, and then leading to permanently deactivation the catalyst. It is the summary of the carbon formation on nickel-based catalyst. The activation of support nickel metal by carbon may occur by chemisorption, carbide formation, physically owing to blocking of surface sites, blocking of pores, and destruction of catalyst pellets by carbon filament. By the way, blocking of catalytic site by chemisorbate hydrocarbon, surface carbide, or relatively reactive films is generally reversible in hydrogen steam, CO2, or oxygen. And it is the last part about research direction. Carbon formation can be avoided when the CO2 concentration in nickel crystal is lower than that at equilibrium, so it can decrease the steady-state carbon activity by first is to enhancing the absorption of steam or CO2. Second is to enhancing the rate of the surface reaction. And the third is decreasing the rate of degree of methane activation and dissociation. First method is to using a promoter to the nickel. The use of promoters can improve the coke resistance of nickel-based catalysts in reforming process. And promoter can affect the reducibility and dispersion of nickel particles by acting as structural promoters and affecting the segregation in reduction process. And it is example of promoter which are interesting for study. First is to use basic sucrose or oxide promoter, which lower carbon deposition rate by preventing hydrocracking and by facilitating absorption of steam. Or second is to use metal such as copper or silver, which lower rate of graphite formation on nickel by decreasing ensemble size. Since carbon formation on metals requires a critical ensemble of surface metals atom. And the another method is changing the support. For example, use anatase titanium dioxide nanosheets or use the aluminated FAU and BEA zeolites as a support. Or second is to use pyrrolylurethrium titanate, leading to the more abundant active oxygen species are present and being beneficial to remove wall of the carbon deposition and keeping the nickel size free from coating. It is the end of my presentation. Thank you for your attention.
Okay, thank you, Jagapan. We have 1 minute left. Next speaker, please. Suticha. Okay, you have 30 seconds. Be prepared. Okay, 10 seconds.
Good morning, teacher and everyone. I am Sutisha Mutinda. Today, I would like to present a report about catalytic deactivation in the topic poisoning and deactivation of palladium catalyst. For the outline, introduction, literature reviews, conclusion, and future research. Uncontrolled and accidental poisoning or activation of palladium catalyst by various mechanisms can be a considerable fission burden in chemical industry and is still on focus of academic as well as technological research. Some tactical large-scale applications of palladium catalyst are their use in the hydrogenation of organic phytochemicals, aromatic hydrogenations, and typical lesson for the activation of palladium catalyst have 5 topics. First, casterite ghost or sintering or accumulation, and second, infusion of carbon, and third, physical property, fourth, poisoning, and finally, leaching. And for the literature review first, this topic about sulfur poisoning of palladium catalyst used for methane combustion effect of the support. This research investigated for 4 different support palladium catalysts are using alumina, silica, zirconium, and titanium as support as test catalyst for methane oxidation in presence of sulfur dioxide. For the synthesis catalyst, followed by discharge, and after that use catalyst to reaction study. For the result in Fig 2, the catalyst supported on zirconia show the best performance, palladium supported on zirconia show similar activity for methane combustion and highly resistant to poisoning by sulfur dioxide than condensation palladium supported on alumina. And next research. This research topic, combustion of methane over palladium-based catalyst, catalytic deactivation, and law of support. This research studied the effect of palladium-based catalysts supported on metal oxide are effective for methane combustion at low temperature below 450 degrees Celsius. To better understand the mechanism for catalytic deactivation. Catalysts used in this investigation were for support. Show this, and a catalyst was prepared by Westnet, prepared by Westnet impregnation, and after that to test for hydroxyl accumulation on palladium oxide and on the support during catalytic deactivation. They utilize in institute transmission FTIR spectroscopy at 325 degrees Celsius. Catalytic deactivation in this temperature regime has been attributed to a water per hydroxyl inhibition effect. Comparative in institute FTIR transmission spectroscopy experiments at 325 degrees Celsius reveal that hydroxyl accumulation occur on the oxide support during catalytic methane combustion and deactivation. Hydroxyl accumulation on the catalyst also hided the catalytic combustion reaction by blocking active catalytic site. A palladium hydroxide bond may exist at around 3,734 centimeters. And next, literature review in topic, study on the deactivation and activation of palladium impregnated carbon catalyst for environmental applications. The aim of this study is to explore different reactivation process for hydrogen sulfide activated palladium impregnated carbon catalyst and evaluation of its carbon monoxide removal efficiency.
2-minute lab.
These research separate for experimental are synthesis catalyst next to catalyst characterization, then enter to hydrogen sulfide poisoning and carbon monoxide removal efficiency study. And finally, the activation of the catalyst was achieved by using sulfur dioxide as the poisoning agent. Fig 7 show breakthrough apart of A, fresh palladium carbon catalyst, and B, deactivate palladium carbon catalyst carried out in the presence and absence of moisture. And Fig 8 show breakthrough part A, formaldehyde treat poison palladium carbon catalyst, and B, sodium borohydride treat poison palladium catalyst carried out in the presence and absence of moisture. Conclusion. Its conclusion, this table presents all paper research concern with the topic poisoning and the activation of palladium catalyst. For future research, poisoning cause first, strong chemisoption of reactants, and second, depending upon the concentration and state on the poisoning agents. And finally, in the case of reversible deactivation, heat treatment, washing, or removal of poison from the process steam, often reactor is catalytic deactivation. The development of palladium-based sulfur-resistant total combustion catalyst would be very interesting from an environmental point of view. It must be considered that even in the case of installation of sulfur tapping device before the combustor,
Time is over.
Finish your presentation. Okay, no, just keep, wrap up. Okay. Okay, continue. Okay. We have 30 seconds.
Small amount of sulfur compound can be slipped into the reaction. Thus, the development of a mechanistic model of predicting the deactivation of this catalyst is also of great particle interest. Okay, thank you for your attention.
Thank you. Okay, thank you, Sudisha. Next, please. This is really good that you use the subtitle for the function in the PowerPoint. Okay, thank you.
Sorry.
Next. We have 3, 2, 1 second. Okay, I think Victor is not here. Victor is not here. Okay. So Muhammad, please wait so that we will be on time, because the next presentation will be on schedule. If we start earlier, they will not know that we shift the schedule. Okay, so you will be starting at 9:25 as your schedule. Okay.
Okay.
Can you test your microphone? Okay. Please test the mic, please.
Can you hear me?
Yes. Okay. So we have like 6 minutes. Who is your advisor?
Achan Mandan and Achan Banjir.
So you're doing the nickel base also or not? Which reaction are you doing right now?
Dry reforming of methane.
Dry reforming methane. Oh, okay. Where are you from?
I'm from Indonesia, Achan.
Oh, Indonesia. Okay. So you're doing the PhD or the master?
Direct PhD, Achan.
Direct PhD. Oh, okay. So everyone, as we have time, please export your presentation to PDF and then upload to the course view. Okay. Mohammed, how was the situation in Indonesia, the COVID right now?
Still, I think it's worse, Asen.
Oh,
Yeah,
so
because
both sides, both islands.
like most of the island is really worse because
Oh,
right now it's like reach over 1 million people got infected.
wow. Oh, and the vaccination is not yet also, right?
It's already been started, Asen. It
Oh,
started.
and in Jakarta is worse or better?
I think one of the worst
Oh,
city.
is it dense? That dense? I mean, the population.
Yeah, Jan. It's really
Oh,
because
oh,
main populations in Java Island, which is also
oh,
in Jakarta.
oh. But they start to vaccinate the people in Bali first to accept the tourists, as I read.
Yes, Jan.
Mm.
And actually, it's yeah in Bali, Jakarta, and also yes, some like the worst part.
Oh, but most of the tourists in Bali came from the Australia or something because it's so near to the northern of Australia.
Yes, and I think
Um,
mostly from Australia.
mm. And what's your plan after the PhD?
Um, I'm not really sure, Jan. Maybe I would like to become like a channel lecturer or
Uh,
researcher.
doing postdoc like in Europe, Australia, or US, something?
Um, I'm not sure, Jan.
Okay. Or doing startups. That's it. Yeah, that works also. In lots of the friends in Malaysia or even Philippines, Indonesia. Gojek is from Indonesia. You know that the new delivery company that is in Thailand. Gojek.
Yeah, Jan.
Yeah, that one came from Indonesia.
Yes, Jan.
Hmm. Okay, we will start in 1 minute. Okay. Okay, please, Mohammed, and use the laser pointer also. Thank you.
Uh, Hello everyone. My name is Muhammad Dodi Istaini. I'm going to deliver about a review about coke depositions of a nickel-based catalyst for dry reforming of methane. So the outline will be introductions and literature review and also conclusions, which will be conclude the whole review and also the research outlook. So the main problem is about the content of carbon dioxide and methane on the atmosphere. So due to the fossil fuel consumptions, but we cannot really get rid of the fossil fuel consumptions because the use of transportations, rapid industrial development, and also global populations. But dry reforming of methane becomes one of the most promising technology right now, and it can because it can convert carbon dioxide and methane into carbon monoxide and also hydrogen. And most widely used catalyst is nickel. So this is I'm going the active site. Active site is the locations where the reactions occur. So it helps to dissociate reactions into products and also facilitate the activation and absorptions of carbon dioxide and methane. And figure 1A, the SEM image of fresh catalyst. So actually this paper explain about the nickel loading effect on alumina oxide. So the first figure 1A is 25% nickel and 1B is 33% nickel. So the research explained that the higher nickel loading, it can promote the high dispersions of nickel catalyst. But if it's like overloaded, like 33, it promotes the decreasing of nickel dispersions. And also the favorable size is the smaller nickel particles will be help to provide more active site on the surface of the catalyst. And this is the basicity and also acidity of surface on the catalyst. So basicity property from a support or a promoter, it can help to activate carbon dioxide and also uh, promote the absorptions of carbon monoxide. So the more basic side on the catalyst, it can help to absorb CO2 because CO2 is acid, Lewis acid, and this is the figure 2 tells about CO2 TPD. So this is the magnesium oxide loading. So the higher magnesium oxide in here, 2% magnesium oxide on nickel alumina, it helps to enhance the basicity property on the catalyst. And also the basicity of catalyst can promote can enhance the hydroxyl group, which also promotes the coke gasification. And this is the support. Like I mentioned before, it increased the total basicity to the catalyst and also to make stronger metal support interactions between metal active site and also the support. So the effect of metal support interactions to disperse active site and also to maintain its uniform size and to prevent the growth of particle size. Actually, this is about sintering as well, and also to provide significant increase of surface oxygen species, which is hydroxyl oxygen, which facilitate to activate and also the absorptions of CO2. And this is the carbon or coke deposition. So the mechanism of the coke depositions coming from methane depositions, which will transform into coke, which is carbon and also hydrogen. And then the second mechanism is coming from these proportions of CO reactions, which also can can create can form the carbon on the catalyst. So this is the mechanisms of carbon formations. So it starts from carbon C alpha or atomic carbon,
2 minutes left.
and then at higher temperature like 250 to 500, it can be filamentous carbon, and it can further polymerize into carbon graphitic carbon. And also the whisker carbon, which is from 300 to 1000, it can also promote the activation process. And the most resistant nickel is nickel with flat surface, which is nickel 111 is the most resistant compared to nickel step nickel 211 and nickel carbide. So the conclusion is dry reforming is really promising road for catalyzing methane and also carbon dioxide, which can also further synthesize via Fischer-Tropsch into valuable chemicals feedstock. And nickel is widely used because high catalytic activity, availability, and low cost. And improving the catalytic activity and stability can be done by tuning various properties on the catalyst, such as basicity, metal support interactions, oxygen vacancy, crystalline oxide, and inner cavity structure when it comes to silica oxide. And the research outlook, actually the main problem from the catalyst that cannot really commercialize because the catalyst cannot really obtain the long-term stability. So it fast it's safer to carbon depositions on the catalyst. So like I mentioned before, we need to adjust like proper adjustment of properties interactions in order to get high catalytic activity, long-term stability, and to meet the cost target. This is the reference, and thank you for your attention.
Okay, thank you, Muhammad. And please send your presentation. And next speaker, please be prepared. Ulanat. Okay. Please test the microphone, and also the pointer.
Good morning, teacher and everyone. Today I will present about activations of nickel and cobalt catalyst in ethanol steam reforming at my temperature in a fluid dye-based reactor. On the outline, 1. Introduction. Coke deactivations is the process with from coke where the coke will flow the surface coke of the catalyst. Effect of cooking have 4 cases. 1. Buckets of active size. 4. 2. Encapsulations and deactivations of the catalyst. 3. Plug the pore of the support. And 4. Catalyst incigations due to state of the coke acting on the wall of the pore. The experiments. The first step, prepare the internship with wet impregnations at 70 degrees Celsius under vacuum using an aqua nickel trunate hexahydrate and silicon dioxide. The solid is dry as 110 degrees Celsius for 24 hours and subsequent calcite in air as 550 degrees Celsius for 4 hours and using lithium nitrate solutions the solids obtained dry as 110 degrees Celsius for 24 hours and calcite as 615 degrees Celsius for 3 hours. And cobalt trunate solutions prepared by internship with impregnations. The solids are dry as 100 degrees Celsius for 24 hours and calcite as 600 degrees Celsius for 6 hours. And characterizations are X-ray diffractions, thermobalance, scanning electron microscope. In the next part is results and discussions. First, the figure 1 shows the evolutions with time on the stream of ethanol conversions and hydrogen yield for the different catalysts in the ethanol stream reforming as 500 degrees Celsius stream per ethanol molar ratio of 6. State time of 0.14 gram catalyst higher per gram ethanol and ethanol particle pressure of 0.11 bar. In the figure 2, show SEM image in the nickel particle. In the figure 2A, nickel particles are observed as at the end of carbon filament whose diameter is similar to the that of the metal particle, which is consistent with the mechanism proposed of filamental coke formation. In the figure 2B, as a high content of coke filaments is observed, which this size being highly heterogeneous in the fractions of particles with higher size more than 630 micrometers. In the figure 3, correspond to particle larger than 630 micrometers of the same catalyst used for 20 hours, and so they contain main filament coke on the outside. The contents of carbon filament is much higher than on the similar particle, and accumulate of from which make it difficult to appreciate nickel metal particle. In the figure 4, for the different deactivated catalyst, confirm this filamental structure of the coke, which is formed by coke filaments, highly heterogeneous in both size and shape. In the figure 5, show the major peak as 500 to 530 degrees Celsius, corresponding to the hydrogenations of carbon filaments, and another major peak as 300 to 350 degrees Celsius, corresponding to another fractions of polymeric and non-structured coke. And the figure 7, carbon filaments are not observed due to low coke contents because it undergoes gasifications at the temperature. In the last one, in the TPO profiles, which corresponding to the coke combustions of catalytic deactivations at 7 degrees Celsius, a major peak is observed, which shift from 605 to 650 degrees Celsius, and coke contents increase and corresponding to the oxidations of highly graphitic coke. In the next part, conclusion. The activations of nickel and cobalt catalyst at 500 degrees Celsius is coke depositions with its constituent by two fractions of different nature, from which gas of monoatomic and polymeric coke absorbed on the metal is main responsible for the activations by coking metallic size, and a higher metal dispersions handle metallic size pockets, which expand the higher stability of nickel catalytic compound to cobalt catalytic. Thank you for attention.
Okay, thank you. The next presentation will start at 9:41. Kelvin, please prepare, but don't start yet. So the person that evaluate Victor, so referee numbers 6 and 7, right? 6 and 7. So Mohammed and Kulanat. So Victor will present at 11:40 today. Yes.
Thank you very much.
Okay, Kevin, please.
Okay, good morning, everyone. My name is Kevin, and today I'm going to give a presentation on the coke formation for nickel metal-based catalyst in dry methane reforming process. So the outline of the presentation today is a general introduction, the literature review, which will talk about the effect of temperature, pressure, and feed ratio on the coke formation, and a general conclusion and the research outlook. So as for the introduction, as you all know, the carbon dioxide emission has been increasing significantly since the 1950s, from 5 billion tons to roughly about 36 billion tons produced annually today. This is where DRM comes into play. If you look at the equation below, you can see that carbon dioxide and methane combine with each other to form carbon oxide and hydrogen gas, which is known as syngas that can be used in other industries. So for the formation of coke in DRM process, the DRM process is an endothermic reaction, meaning that high temperature is needed to achieve a desired conversion. Normally, non-noble metal catalysts such as nickel are used due to its lower cost and availability, but it is more readily to deposit coke on its surface, so it will lead to rapid deactivation of the catalyst. The side reaction that forms coke during the DRM process is as follows, which is these four equations right here: the decomposition of methane, the disproportionation of carbon monoxide, and the last two is hydrogenation of carbon dioxide and carbon monoxide. On to the literature review. So the effects of temperature are split, normally is split into two sections, which is endothermic and exothermic. So the four equations that we've seen just now, we split it into both, which is endothermic, which prefers high temperature. You can see on the graph here, high temperature means higher temperature, higher formation of coke, and exothermic, lower temperature, higher carbon deposition. So as you can see here, if we were to adjust our temperature to a slightly higher temperature, we can actually eliminate all three of this equation and only focus on one, which is being done. And as you can see in this figure below, if we increase the temperature from 650 to 750 and 850, the initial and final conversion of methane actually increases significantly. This draws a conclusion that the DRM process at higher temperature have a high conversion and resistivity to coke for the nickel-based metal catalyst. Next is the feed ratio. Feed ratio meaning the feed ratio of carbon dioxide to methane. So more than 1 and less than 1. So as you can see in the figure here, if it's more than 1, so meaning 1, 2, 3, the coke deposition decreases as the temperature increases. However, if the feed ratio is less than 1, the coke deposition actually remains constant even at high temperature. So the reason for this is at feed ratio more than 1, carbon dioxide is excess and methane is limited. So carbon dioxide will combine with carbon to form carbon oxide, reducing carbon. But with methane limited, the carbon formation will not happen. Oppositely, for less than 1, carbon removal would happen and carbon deposition will happen. So to draw a conclusion for the feed ratio, we can see that the fit ratio of more than 1 and a high temperature is needed to minimize the formation of coke. So for the effect of pressure, we split it into higher pressure and lower pressure. So if you look at the figure on the left, if you pick a line which is a constant temperature, as the pressure increases from 1 to 25 atmospheric, the carbon deposition increases as well. So the reason for this is if we are taking the fit ratio more than 1, methane will be limited. So the first equation, we don't really need to focus on it. So higher pressure in the literature shows that it encourages the disproportionation of carbon dioxide. Lower pressure discourages the disproportionation of carbon dioxide. So if you look at the DIM process, carbon dioxide is a main product. So in the end, it will produce excess carbon dioxide. So if the lower pressure were to discourage this equation, it actually produces lesser coke compared to higher pressure. Thus, lower pressure at around 1 atm and a high temperature, according to this figure, is favorable to minimize the formation of coke. So as a conclusion and the research outlook, conclusion is the DIM process has a high potential to reduce the two major greenhouse gases, which is methane and carbon dioxide, to useful and valuable syngas. So to conclude the review is the study on the effect of temperature, pressure, and fit ratio on the deposition of carbon on the catalyst. The general rule of thumb that we have found out is the temperature should be around 800 degrees and above, the pressure around 1 atm, and the fit ratio should be more than 1 for the current catalyst that is being tested on now. So for the research outlook, I believe the end of the goal of this research is to make the carbon deposition becoming negligible to proceed to fully industrialize the process. So four main
2-minute left.
Four main recommendation has been placed. Firstly is the more variation testing on bimetallic catalysts. Next is the discovery of brand new catalysts. These two mainly is to find new catalysts that can perform better in terms of reducing the carbon deposition. Next is the physical properties of the catalyst, mainly size and arrangement should be focused on. And lastly is the longer hours of stability and operation testing, as in the industry needs a longer stability time and operation to make the process feasible. So I think that's all for my presentation. Thank you.
Okay, thanks, Kelvin. หรือว่ามันมีเสียงแทรกตลอดเลยอะมันเป็นเสียงซ่าๆเราลองใช้หูฟังเสียบไมค์ได้ไหม
ใช้หูฟังอยู่ครับ
หรอเสียงมันซ่ามากเหมือนเสียงลมเข้าอ่ะ
หายยังครับ
เหมือนเสียงลมเข้าอ่ะเสียงแอร์ป่ะ
สักครู่โอเคขึ้นไหมครับ
ก็ดีมันยังมีเสียงเหมือนลมเป่าตลอดเวลา
อ๋อมันเป็นเสียงของโน้ตบุ๊กครับ
โอเคเสียงโน้ตบุ๊กโอเคไม่เป็นไรwe'll start at in 1 minute okay please go
okay good morning everyone my name is Jirawat Chu Sang today I'm going to present the topic of the regeneration process of platinum SN on alumina catalyst for propane dehydrogenation. I have divided my presentation in these following sections. The first one, introduction, next, literature review, and the research direction of this work. Let's begin to first part, introduction. Propene or propylene is important chemical intermediate or building block used to produce a widely bought chemicals, including biofuel, pharmaceutical, and especially polymers for polyethylene. The primary process for produce propylene is propane dehydrogenation or PHD. The platinum catalyst is popular catalyst for PhD reaction because environmental impact of chromium-based catalysts that tend to decrease its usage. This reaction is endothermic that require high temperature. This cause lead to major problems as catalytic deactivation include cooking and sintering. Therefore, it is important to develop the effective regeneration process for PDH to obtain long-term activities. So the objectives of this work are to study and compare the regeneration process of platinum catalyst for PhD reaction and to develop the regeneration process of platinum catalyst. Here is the literature review. For this paper in 2018, they investigate three processes of regeneration include hydrogen purging, nitrogen purging, and redox to find the best process for regeneration platinum SN on alumina catalyst in PhD reaction. The catalytic performance during periodic reaction regeneration cycle using different regeneration modes are shown in figure 1. The propylene selectivity over the catalyst regenerated by redox was slightly higher than regenerated by hydrogen or nitrogen purging. After 11 cycles, the propane conversions over regenerated by hydrogen purging show the highest conversion. Therefore, the catalyst using hydrogen regeneration show the best stability. The reason for hydrogen process is the best stability are expanded in catalyst characterization topic. First, the HAADFSTEM image and metal particle size distribution are shown in figure 2. After 11 cycles, the particle size of regenerated by hydrogen and nitrogen no significant sintering emerged, whereas for the regenerated by redox, particle size increased to 70 nanometers. That show this method lead to metal accumulation. Next, the XRD results show not only metal accumulation but also phase transition to platinum 3SN. Last picture show HRTEM image. The lattice spacing in the shell region S-kind to SN suggests that the metal SN possible constitute the shell. This SN encapsulation inhibits the activity. For this section, the amount and property of coke over spent catalyst show in table 1. The results show about 10% coke deposit on hydrogen and nitrogen regenerated for turbo the pore of alumina support, while no coke detected on the redox method. Additional from CH results show nitrogen purging remove coke by volatilization only less dense coke, but hydrogen purging can remove residual coke by hydrogenation. The conclusion of this paper, the using nitrogen or nitrogen regeneration result in the return impact on the size and structure of metal active center. In part of redox regeneration can completely coke removal, but inhibits pore stability due to metal accumulation, phase application, and core structure with SN-rich surface. For next development in 2020, they use halide solution after coke burning process. It can cause oxychlorination to redisperse the metal particle. This method shown in figure 5. The conversion recovery shown in this picture is more demonstrate that secondary regeneration with HCl treatment was higher conversion recovery than only coke burning, and figure B show that no significant change in selectivity recovery for three catalysts. For catalytic characterization, EDX and TEM image of catalyst shown in this picture. The particle size of metal increase after coke burning. HCl treatment can reduce the size of metal particle. The highly depositivity of metal particle was observed in 35% HCl concentration. And table 2 present the CO chemical solution in 35 HCl had the highest metal surface area. Smallest particle size and the hole formation was reduced. The conclusion of this paper, HCl treatment can improve the regeneration process include redispersion of platinum particle, change interaction between platinum SN and HCl. The last part is research direction. From various literature from past to present, I integrate the advantage and disadvantage for each method that shown in table 3. For PDH reaction with platinum SN on alumina catalyst, the hydrogen purging is also interesting because not required for switch gas after reaction. That's important for industrial process and return impact on metal particle size and metal phase change. But this method still has some disadvantages, such as this method cannot completely co-removal. So this method is still the future development, and table 4 show the role of SN that can reduce co-formation on metal side and emphasize platinum redispersion. And the last one, the future developed for platinum SN on alumina regeneration that I conclude in 3 topics. First, the modification of platinum on alumina catalyst with other material or other synthesis method that can reduce coking or sintering. Next, the optimization for regenerate catalyst and integrate into one-step process. For example, using partial oxidation for helping coke burning with reduce the metal phase change. Last topic, that the development regeneration process or reactor for solving root cause of reactivation. Thank you for attention.
Okay, thank you, Jirawat. Okay, Shannon, you start in 1 minute. Okay, Shannon, start.
Good morning, teacher and the other audience. My name is Shannon Bunsaksit. Today, I will represent the topic about the activation of the copper catalyst of ethanol dehydrogenation for the acetaldehyde production. Okay, let's see the first section is the introduction section. The acetaldehyde is the main phytochemical product used as the preservative and flavoring agent in the food engineering, and it is the important feedstock for the production of many other high valuable chemicals. Two gas phase process for the conversion of ethanol into the acetaldehyde have been described in the literature review. The first is the selective oxidative with air, and the second is the dehydrogenation process. And when we compare in the two processes, show the dehydrogenation process is the promising route for the acetaldehyde production. The catalytic dehydrogenation is especially of advantage with primary alcohol because it prevents over-oxidation of the carboxylic acid, and the produced acetaldehyde from the dehydrogenation reaction is easily further separated by the byproduct of the reaction, and equivalent amount of the hydrogen are obtained as the co-product. Generally, the catalytic of the alcohol dehydrogenation can be mainly divided into the two types, including the metal and the metal oxide. Among these catalysts, the copper-based catalyst is shown the high efficiency and selectivity for the non-oxidative dehydrogenation of the ethanol to acetaldehyde because the carbon and carbon bond are at much lower rate than the other transition metal. But unfortunately, the initial high activity of the copper catalytic decelerates rapidly for the catalytic deactivation. And the operating process for problem found the dehydrogenation catalytic is converted to the dehydration catalytic while the catalytic is used more cycle. And the objective of this presentation to show the previous article how to improve the copper catalytic performance and reduce the catalytic deactivation problem. Okay. Although copper catalytic exhibit very high activity and good selectivity for the acetaldehyde, the catalytic deactivation is the main problem for the ethanol dehydrogenation due to the short stable time in which cause both co-formation and the synthesis. Nowadays, many researchers have investigated how to improve the catalytic performance and reduce the deactivation problem. The first alternative is the selection of the support material. This figure shows the catalytic activity of the copper catalytic in terms of ethanol conversion and the main product used as the acetaldehyde at the different support material. The copper alumina denoted by the star symbol show the base performance of the ethanol conversion when we operate in the high temperature. But when we see the result of the yield of acetaldehyde show the yield of the copper alumina had the lowest when we compare with the other catalytic. And moreover, when we see in the second cycle show the copper alumina has the poor performance in the yield production of the acetaldehyde. In the other hand, when we see the result of the copper zinc aluminate denoted by the circle symbol, show the show the base show the base yield of the acetaldehyde when we operate in the second cycle, and the result provide similar when compared with the first cycle. Even though the zinc aluminate copper is the slightly lower than the copper alumina when compared the ethanol conversion. And the second alternative is the addition of the promoter. The promoter can help for reduce the copper particle size co-formation inside the pore catalyst and increase the catalytic stability. And in this figure show the result when we compare the promoted catalytic and unpromoted catalytic. The result show when we promote the copper with the magnesium show the deactivation rate of the catalytic is lowest when we compare the
2
unpromoted.
minutes left.
But in contrast, when we use the author promoter show the poor performance when we compare with unpromoted catalytic. The result show the suitable promoter can enhance the catalytic stability. And the final alternative is the different synthesized catalytic method. The synthesized catalytic method can help the catalytic stability. In the figure show the activity of the ethanol dehydrogenation of the copper support by silica. When we the different synthesized catalytic method, the result show the ammonia evaporation method has the best performance and the long stability time when we compare the other synthetic catalytic method. Now let's move to the summarize section. The deactivation stream of the carbon-based catalytic found the coking and the scintillating appear to the dehydrogenation reaction of the ethanol. The main problem of copper-based catalytic is low stability, although there is the high initial catalytic. And the conclusion of the reducing problem of the catalytic from the present show the three topics is the selection of support material, the acquisition of the suitable promoter, and the different synthesis catalytic. All of this influence for the catalytic deactivation. And thank you for your attention.
Thank you, Shannon. Okay, we have 2 minutes left. Napat. And please turn on your video. Napat, test your microphone and we cannot hear you.
Okay.
Okay. 1 minute. ไก่ที่บ้านเหรอ Okay, please go.
Okay. Good morning, teacher. My name is Napat Orarashin. Today I am here to talk to you about co-formation during steam reforming of acetic acid for hydrogen production. And then I'm going to start with content. The first is introduction. Second is co-formation mechanism during AASR. And the last, conclusion and research direction. Next is chapter 1. I will talk about introduction. Hydrogen as a clean fuel is recognized as the most promising future energy alternative for transportation due to its high energy density, 122 megajoule per kilogram, and environmental friendly nature. Figure 1 show the reference source of hydrogen generation. Biomass derived biofuel obtained from thermochemical process such as fast pyrolysis of biomass has been projected as a renewable source to produce hydrogen by steam reforming. Next is show the equation. ASR for hydrogen generation. Equation 1 can take place via acetic acid decomposition. Equation 2 followed by water gas ship reaction. Equation 3. Okay, and then acetic acid is one of the major fraction of bio-oil. Acetic acid may be used safely for hydrogen production as it is not non-flammable. For this reason, acetic acid is often selected as a model compound for bio-oil for studying hydrogen production via steam reforming. Figure 3 show the detailed schematic representation of hydrogen generation from biomass derived bio-oil via steam reforming reaction. Next is chapter 2. I talk about coke formation mechanism during AASR. A simple reaction mechanism of AASR proposed in several studies is shown figure 4 and figure 5. The dissociation of acetic acid over the catalyst surface is shown along with the proposed bifunctional mechanism. Dissociation of acetic acid over active metal phase takes place by cleavage of CO and OH bond. Meanwhile, interaction with acidic support site ketonisation reaction might occur that is followed by oligomerization of acetone, resulting in co-formation not only over the support but also over metal support interface. The figure 6 show the TGA and DTA analysis. That for 15 nickel alumina catalyst, oxidation of carbon start at 400 degrees Celsius and continue at 670 degrees Celsius. On the other hand, for 15 nickel magnesium alumina catalyst, oxidation of carbon start at 100 degrees Celsius and end at 670 degrees Celsius. For both the sample, most of the deposit carbon remain over the catalyst surface at 500 degrees Celsius. The peak at 350 degrees Celsius was due to the removal readily oxidable carbon species and disruption of water and carbon dioxide from the catalyst surface. Okay, next is effect of operating condition on reforming reaction. A typical result showing the effect of steam to carbon ratio given in table 1. Results show that relatively low carbon balance is obtained at a lower steam to carbon ratio. Low steam ratio favor decomposition of feedstock that result in the formation of a large number of my product which act as a precursor during coke formation. Okay, and then effect of type of reactor. A modified dual bed system in series of AASR. In figure 7, the bare catalyst surface show activity only toward acetic acid ketonization reaction and form comparatively low coke deposition during AASR. in case of dual bed configuration utilized for AASR, wherein the first bed acetic acid convert to acetone via ketonization reaction with further undergo steam reforming in the second bed. The improved stability of the catalyst system could be because the steam reforming of acetone resulting in less coke deposition in contrast to acetic acid, and also there was an increase in steam to carbon feed ratio. Okay, next is chapter 3, conclusion and result direction. First, incorporation of small amount of oxygen during reforming reaction also help to minimize the coking by gasify the carbon deposit over the catalyst surface. Second, encapsulation of carbon catalyst surface with the coke result in severe catalyst deactivation. The third, free bed reactor and dual bed system in series during ASR show lesser coke deposition compared to fixed bed reactor. And the last present summarize a broad analysis for the reduction of carbon formation using suitable catalyst and support type of reactor, result in increased catalyst life. Okay, thank you for your attention.
Okay, thank you, Napat. So we have 2 more minutes. Nathanon, please prepare your slide. Okay, Nathanon, start at 10:12. Okay. Nathanon, turn on the video, please.
Okay.
Okay, start.
Okay. Good morning, everyone. My name is Nathanon. Today, I would like to present about nickel-based catalytic regeneration from sulfur poisoning. In this presentation consists of 3 parts. First is introduction to explain about hydrogen production, nickel catalytic and poisoning. Second is the literature review to show about the regeneration, and the last is conclusion to show the future direction. Nowadays, there are many ways to produce hydrogen, whether it be electrolysis, coal, oil, but the major way is come from the natural gas, which used in the methane reforming to produce synthesis gas. And to improve the performance of production, nickel catalytic production of process catalyst must be used because of abundance, low cost, and high activity when compared with the noble metal. Nickel-based catalyst is suitable to use in this reaction. However, the component in natural gas contain not only methane, but also other substance that may affect to the methane reforming, such as hydrogen sulfide. This chemical can make the strong absorption on the nickel catalyst. And from this absorption, the active site was blocked by sulfur, so the reactant cannot absorb and cause the result in the reduction of activity. To get back the active catalyst, the regeneration process was applied to solve this problem. And there are many ways to regenerate catalyst. The one way was presented in this paper, which show in the regeneration method from Raju petrochemical. The steam treatment was used co-feed with hydrogen. Steam will reduce the sulfur from nickel catalyst, and hydrogen will change the nickel oxide to nickel metal form. The result from study was shown in the ratio between sulfur content before and after regeneration. And when the ratio between vapor steam and hydrogen increased, the regeneration increased too. It means to get back the high activity, the high ratio between vapor and hydrogen is required. However, this process takes a long time to eliminate sulfur. Another paper was shown to confirm about sulfur poisoning and steam treatment. The results show that sulfur can easily absorb on the nickel catalyst at low temperature, and the regeneration results show that it spent 6 hours in regeneration. To improve the high performance of production and reduce the regeneration time, this paper will apply the thermal recuperation process of exhaust gas, and the steam treatment was replaced by oxygen treatment. Moreover, in the reactor consists of 3 reactions: mid stream reforming, dry reforming, and partial oxidation is called dry reforming. And this process, there are 2 operation modes: reforming and regeneration. In reforming, the reactant were heated by exhaust gas, which came from furnace, and some of exhaust gas were recirculated to the inlet feed to fix the ratio between methane, vapor stream, and carbon dioxide. In regeneration mode, the hydrogen and oxygen were heated by exhaust gas too, but the circulate line was closed, so the exhaust gas were sent to chimney. The result of sulfur poisoning showed that the deactivation was caused by the sulfur chemisorption from hydrogen sulfide and sulfur dioxide, but hydrogen sulfide has more effect than sulfur dioxide in every content. And the regeneration results show that it spent about 4.2 hours in regeneration step. That is lower than steam treatment. So let's move to the future direction. For now,
2 minutes
the
time left.
effective way to regeneration nickel catalyst is oxygen treatment. However, the regeneration must be enhanced moreover. So from the literature review, I think there are 2 possible ways to develop the regeneration process. First is the lower regeneration time, such as development the process that better than oxygen treatment, or the development the catalyst that the regeneration can occur during the reaction. And the second way is the energy saving, because steam treatment and both reforming, methane reforming, and the regeneration process use the high condition. So the regeneration process at low condition will save the operating cost or other. Thank you for your attention.
Thank you, Nathanon. We still have time, 2 minutes. Okay. And I would like to ask you to write one question uh, for your speaker that you are evaluating. In the last box of each speaker, there's a comment box. So in that box, instead of writing a comment, you have to write the questions. and then I will distribute to the speaker and let them answer. And this will be evaluated also together with the report. Okay, if you have any questions, again, ask it in the discussion box. And also I will upload the today's presentation to the YouTube and upload to CourseView the same. Okay, Natapat, please prepare your slides.
Okay, can you hear me?
Okay, you will go in 15 seconds. Turn on the camera also. Okay. Okay, please start now and share your screen.
Hello everyone, my name is Natapat Kabasit. Today I will present talking about improvement the stability of the catalyst against corking. Sorry, wait a minute.
Okay, no problem. Okay, and use the laser.
The
Control
outline
R.
contains introduction, literature review, and conclusion. The first part will show why coke is so important for chemical process. Coke is the carbon that's formed from the substance in the reaction. With coke will result in bucket and encapsulating active site, back the pore of the support, and disintegration of catalyst. From the effect mentioned above, if the process has coke, it will result in the catalyst loss active site and activity. Finally, it will result in a loss of profit due to degeneration process. In the literature review, I will study the direct forming of methane reaction, which convert methane and carbon dioxide to syngas using a nickel catalyst. But this process has forming of large amount of coke due to the hydrocarbon substance. So more stability of catalyst have to be developed from pure nickel catalyst. The first literature review. This is using of nickel catalyst based perovskite. I will show paper about nickel based lanthanum oxide perovskite in reforming of methane reaction. This paper will show that using pure lanthanum perovskite will cause carbon growth, and when regenerating catalyst it lost some active site. From the experiments, manganese addition reduce coke formation and make it easier for the oxygen from lanthanum oxide perovskite to react with the carbon on the active site, so that when regenerating, the active site is not lost. And then is the using of nickel-based catalyst doped with a transition metal. This paper study the mechanism of reforming reaction on the surface of nickel titanium oxide catalyst in a humid environment. During the reaction, two phenomena could be seen. That is the migration of oxygen ion inside titanium oxide and the existence of lactic oxygen at the interface of titanium oxide. The latter react with the deposit carbon to form carbon monoxide, reflecting the positive impact of lactic oxygen on the eliminate of deposit carbon. In addition, in the humid reaction environment, the generated steam can occupy the oxygen vacancy and absorb on the surface of titanium oxide, facilitating the removal of carbon deposit. Moreover, the absorption of water can effectively lower the reaction energy and facilitate the occurrence of the reaction. And then the using of nickel-based catalyst support by rare earth metal oxide. This paper explains that the interfacial oxygen of cerium oxide promote the regeneration of the active site and accelerate the carbon removal, leading a good stability of catalyst because cerium can be reversibly converted between cerium trication and cerium tetracation in the reaction.
2 minutes.
During the direforming of methane reaction, cerium tetracation will be reduced to cerium trication and oxygen vacancy will be generated. This improves the mobility of lactic oxygen to generate coke. Finally, the conclusion: increase the coking resistance of catalyst can be done in many ways, but whichever way we choose, we need to consider the activity of reaction along with it to make the real catalyst stability. Thank you for your attention.
Thank you, Nathapat. Okay, Nathamon, please prepare your slide. You have 1 minute to prepare. And check the microphone and the camera also. And check the laser pointer also. Okay, you have 30 seconds to prepare. Okay, please begin your presentation.
Hello, my name is Nathamunyang Jimnong. Today I present the activation of cobalt molybdenum on alumina oxide catalyst via hydrogenation. First introduction, the cobalt molybdenum catalyst on alumina is widely used in the petrochemical industry, especially in the process of separating sulfur from hydrocarbon compounds to keep the fuel clean, to reduce pollution. Also, this type of catalyst has been developed for use in hydrogen sulfide treatment system.
When the catalyst is in the metal sulfide form, then it ready to undergo hydrogenation with tail gas from the cross process. For sulfur dioxide and sulfur gas are converted to hydrogen sulfide gas by hydrogenation on the surface of the catalyst. Carbonyl sulfide and carbon dioxide are converted to hydrogen sulfide by hydrolysis reaction. Next one is literature review. First, this research has been studied about the hydrodesulfurization or HDS catalyst on gamma alumina oxide with very amount of lithium ion. After sulfidation of cobalt molybdenum phase transformed to very small crystal, the progressive reduction in the interaction between the cobalt phase and the carrier, a marked decrease in the catalytic activity with increasing lithium ion contents was found. Next one is hydroprocessing catalyst regeneration and recycling. This research study about typical cause of the activation of hydroprocessing catalyst. It is generally admitted that there are three causes of catalyst deactivation, the main one being by far coke formation. The second cause may be by the damage of active phase structure and dispersion, while the third one is contamination by various chemical with adsorb on the active site. The coke deposition is most common, followed by poisoning and active phase sintering, as shown in the table 1. This statement is true. Some catalytic process used in refinery. Next one, this paper is study about a series of cobalt molybdenum on alumina oxide hydrodesulfurization catalyst during a year commercial run. The study about catalysts with different loading have according to the research, it was found that active site of cobalt molybdenum barrier sulfide are located at the edge of molybdenum disulfide layer decorated with cobalt. The molybdenum disulfide stack growth in the lateral direction but do not grow in the normal direction to the layer during the HDS run, on the assumption that these clusters are highly active with increased loading. The catalytic activity significantly decreased by aggregation. From the table 2 is summarized the amount of carbon, nickel, and vanadium decomposition on the used catalyst. Next one is this research study about the effect carbon nanotube and alumina support on the catalyst performance. They are found that the main active phase on surface of CNT is molybdenum dioxide, whereas the molybdenum dioxide on the surface of gamma alumina oxide. Catalyst activity tests show that the sulfur content in the product for CNT support cobalt molybdenum catalyst is lower than that the alumina support cobalt molybdenum catalyst. The last one is this research study about the activation of commercial hydrogenation catalyst C999. The spent catalyst exhibit the remarkable decrease of the surface area and pore volume compared to the fresh catalyst. Based on the decreased surface area can be attributed to the sulfur superficial layer conveying on the catalyst surface. When the tail gas treatment system is normal state, the exothermic reaction of this system is caused by smaller sulfur dioxide, but if it is dropped into oxygen entering in the system will undergo violent exothermic reaction and caused by catalyst deactivation. Next one is conclusion. It is generally admitted there are three causes of catalyst deactivation, including first, coke formation from incomplete combustion, second, sintering of metal, The last one is poisoning by various chemical which absorb on the active site. Research direction. Vary the dope of metal and effect on the activity on the catalytic activity. Second, study about the different loading to prepare catalysts. Third, catalytic activity stage show that type of support of cobalt molybdenum catalyst. Study about type of supports also affect the dispersion of catalyst. The last one is catalyst temperature must be controlled. Thank you for your attention.
Okay, thank you, Ratamon. Okay, we have 2 more minutes. Let's start at 10:36. Fifteen seconds.
Good morning, ladies and gentlemen. My name is Nishkan Miguel, and I am pleased to be here today to talk to you about cold deactivation and regeneration study of HSY zeolite catalyst. Introduction. In industrial catalytic process, coke deposition can cause catalytic deactivation by covering acid site or working for the regeneration of the activation catalyst, thereby removing the coke and simultaneously restoring the catalytic activity is highly desired. Several improved regeneration methods can remove coke at low temperature, maximizing regeneration efficiency with minimum catalytic detraction. Coke deactivation. The main deactivation cause is soft coke confinement of the catalytic matrix, which depend on the reaction condition. Hence, there are 2 types of coke. The first one, soft coke, and 2 types of hard coke in the catalytic matrix and in the zeolite micropore. Catalytic regeneration. The coke combustion occurs between 400 degrees Celsius and 700 degrees Celsius. The coke combustion depends mainly on the accessibility of oxygen to the coke rather on the redox and acidic property of the bifunctional catalyst. The accessibility and coke content are strongly related. The regeneration was carried out under mild conditions at 500 degrees Celsius for 20 hours. Despite the low temperature used, all coke molecules were removed but only the portion of the acidic property are recovered after regeneration. In addition, the second regeneration step leads to a radical change in acidic property, mainly for Lewis acid site and site loss of zinc content. Reaction regeneration cycle. The first one, sweeping with nitrogen. Sweeping with nitrogen at 400 degrees Celsius for 1 hour, and the second coke combustion with a continuous flow of air following at heating ramp of 10 degrees Celsius per minute up to 500 degrees Celsius for half an hour. For soft coke, a great amount of retained soft coke are removed after this sweeping treatment, which is evident by the decrease in the intensity of the absorption band. This observation reveals that the main cause of the catalytic deactivation observed in the early stage of the reaction in the confinement of soft coke in interesting about band is observed after sweeping characteristic of more evolved polycyclic aromatic compound remain as hard coke. The main cause of not achieved as sweeping recovery of the physical and acid property is the presence of hard coke on the acid side. Hard coke, two fractions of hard coke, the first one burning at low temperature and the second burning at higher temperature. Therefore, its combustion takes place at higher temperature because of content improved by shape selectivity. Third, hard coke that remain after sweeping will require a subsequent combustion step for this complete removal. For sweeping at a continuous flow of nitrogen on this condition, this sweeping is set to coke combustion, aiming to remove most of compound in the catalytic product structure. And the figure show as observed by removing confined soft coke, the initial activity is almost recovered as well as the initial product yield.
2 minutes left.
For coke combustion with continuous flow of air on this condition, as seen, the catalyst recover its activity and the evolution of conversion as soft coke yield with time on stream with the regeneration catalyst are similar to those obtained with fresh catalyst. For new role for complete regeneration coke zeolite, alternative technology to overcome the difficult associated with thermal regeneration of coke zeolite, non-thermal plasma can be considered as one of the most promising technology. A complete regeneration of zeolite can be achieved at room temperature with a low energy consumption. The coke zeolite was treated under the plasma descent using an airflow of 100 milliliters per minute. The figure shows that plasma treatment leads to the partial coke elimination since the disc presents the gray color compared to the black color of the coke sample. And two figures show that coke partial removed after only few minutes of plasma treatment. Thank you.
Okay, thank you, Nishaka. Next, Thanaporn, please share this slide and test your microphone and video.
Okay.
And we'll start in 1 minute. Where's your name on the slide? Okay, please start.
Okay. Good morning, everyone. My name is Thanaporn Jokloy. Today, I would like to present about regeneration of catalytic deactivation by coke deposition. I distribute this present in three parts. The first part is introduction. Second part is literature review, and the final part is conclusion. Introduction. The big problem of catalyst use is catalytic deactivation, such as coking, sintering, poisoning, and crashing, that affect to catalyst activity and product selectivity decrease, and this presentation focus on the coke deposition. Effect of coking. Coking will block active sites, encapsulate catalyst, and block the pore of support. From previous slide, the catalytic activity is lost when coking occurs, and the solving of this problem is catalytic regeneration. In literature review, I correct this review for the overview the regeneration of catalyst, and this review show the way of coke removal in three ways. The first way is oxidation, second way is gasification, and the last way is hydrogenation. By the oxidation, we freeze air or oxygen for coke removal. The gas production of this reaction is carbon dioxide, carbon monoxide, and water. And gasification feed with carbon dioxide or water. Then they get carbon monoxide as a gas product. And the last one, hydrogenation, is feed with hydrogen that get methane as a gas product. In this paper, show about nickel hydroxyapatite coking. The reaction of this paper is direforming, and this reaction have many side reactions that make the coke occur can see at equation 2 to 4. This paper compare the coke removal between freeze air with CO2, and the result of methane conversion and hydrogen selectivity is slightly decreased when regenerate catalyst compared with base catalyst. That show the successful of catalytic regeneration, and the result show the air regeneration is quite similar than CO2 regeneration. The next paper. This paper refer about coking and regeneration of nickel catalyst. This paper used in cracking reaction at 700 degrees Celsius for 0.5 hours, and you can see from the equation, the coke will occur as a product of this reaction. And this paper regenerate the catalyst from full cycle that regenerate by air at 600 degrees Celsius for 3 hours. From the toluene conversion, results show the decrease of conversion when catalyst is not spaced. But in regeneration first cycle, the conversion is 27%, that nearly with space catalyst. But in full cycle, the conversion is dropped to 16.3%. This slide shows the XRD pattern. In figure 3, show XRD pattern at reaction time, and can see that the peak of carbon is occur when 30-minute runtime. And in figure 4,
Show the XRD pattern, compare the regenerate catalyst with phase catalyst. Found that the peak of nickel alumina will
2 minutes
decrease
left.
and the peak of nickel oxide occur. That means nickel alumina change to nickel oxide and effect to catalytic activity is stopped. And from nitrogen physics option, show the decreasing of power room and surface area that is significant coke occur or accumulation of catalyst. And the final part is conclusion. The regeneration of catalyst is the good way to solving when catalyst deactivates. The first, normally the regeneration of catalyst have three methods: off on gas feed in regeneration process. The second, the popular regeneration is oxidation method, which feeds air or oxygen for coke removal. The last one, the limitation of regeneration is the cooking of catalyst when used high temperature because the structure of catalyst is not stabilized or accumulation of catalyst. Thank you for your attention.
Okay, thank you. Next one, Thamason. Please share your slide, check the video and the microphone. Why is everyone doing the reforming? Huh? Don't you have some like fascinating reactions? Okay. We'll start in 1 minute. You will start at 10:52. Okay.
Good morning, I'm Thamason Thamintakul and I will present the regeneration of nickel-based catalyst for steam methane reforming. In my presentation, I will talk about steam reforming of methane, nickel-based poisoning catalyst regeneration, and bi-reforming. The steam reforming is the one most used important method for production of hydrogen. The reforming production in industrial operate at a high temperature over the nickel-based catalyst. The nickel-based catalysts are efficient but sensitive to poison. Catalyst deactivation, the direct interaction between sulfur from the hydrogen sulfide from feedstock and the nickel catalyst active site. The actual deactivate mechanism depends on the hydrogen sulfide concentration. At the low concentration, are deactivated via the sulfur physics sorbed into the catalyst surface, thereby blocking off access of the reactant to the active nickel site. At the higher concentration, the chemical potential sulfur increase. This favors the chemization of the sulfur into the nickel-based catalyst, lead to the subsequent sulfidation reaction to give nickel sulfide on the catalyst surface. After that, we will consider the catalyst regeneration. The first method is removal of hydrogen sulfide from feed. Since absorption is a reversible process, surface absorb sulfur to be removed by the decreasing the hydrogen content in the feed stream. In the figure show the methane conversion as a functional of time for different hydrogen sulfide concentration. They have performed the regenerate experiment for 100 ppm and 50 ppm by removing hydrogen sulfide at 8 and 11 hours respectively. However, full generation could not be achieved, and the time required for regeneration is around 10 hours. The catalyst activity lost after the regeneration is mainly to the chemism of hydrogen sulfide on a nickel. The second method is a temperature enhancement. The results show the catalyst is almost completely activated in the presence of 100 ppm of hydrogen sulfide at 700 degrees Celsius, and the catalyst begin to recover activity at 800 degrees Celsius and stabilize at the 30%. Finally, the hydrogen sulfide is removed from the feed gas at 800 degrees Celsius, and the methane conversion is stabilized at 95%. The results show that increasing the temperature can be well used to the regenerate of the catalyst poison, and indicate that the increasing temperature can be improved the reversibility of the absorption of sulfur. The third method is steam treatment. The sulfur poison of nickel is regenerated by steam air and steam hydrogen treatment. We had attempt to regenerate treating it with steam. The steam treatment leads to the oxidation of nickel sulfide to nickel oxide, and the catalyst feature reduce nickel oxide to the active nickel site under the hydrogen condition. The results show the steam treatment. The total regeneration time is 10 hours with 5 hours oxidation and 5 hours reduction, and the catalyst full regeneration after the steam treatment. The next topic is tile reforming. Tile reforming is a new process for the production of hydrogen from methane. This
2
process
minutes left.
steam reforming, dye reforming, and partial oxidation of methane in one reactor using nickel-based catalyst. The results show of the steam reforming with oxygen treatment. The regeneration mode started with the injection of oxygen and increase the carbon monoxide and carbon dioxide refer to the carbon content indicate combustion coal deposit. After some minutes, the carbon deposit didn't detect any combustion product, and nickel were complete oxidized to the oxidation nickel oxide. After the oxidation, the reactor filled with the hydrogen and nitrogen to reduce nickel to pure nickel. Finally, the tile reforming were again performed to investigate the activity of the catalyst regeneration producer, and increase of the catalyst activity were observed with the time until the catalyst regenerate full activity after 2.4 hours of tile reforming. Conclusion: the tile reforming regeneration experiment use oxygen treatment and reduction of the catalyst by hydrogen. To perform the results show the full catalyst regeneration with 4.2 hours, which represent a significant improvement in the duration of the regeneration compared to the catalyst regeneration by removing hydrogen sulfide from feed. temperature enchantment, and steam treatment. All of content can be found in the reference biology research paper. Thank you for your attention.
Okay, thank you, Thamason. Tanjira.
Okay.
Okay, you have 1 minute, and you start at 11. I think the gamma alumina is wrong. That's the capital gamma. You should use this the non-capital one for the alumina. Do you understand?
Yes, understand.
Yes, please correct. And please correct it in the report also. Okay, please start.
Good morning, teacher and everybody. My name is Tanjila Thai. Today we are going to talk about cold derivation and non-oxidative dehydrogenation of a vanadium oxide based on catalyst. Sorry. The topic have a ขอโทษนะคะ
ไม่เป็นไรค่อยๆทำ
The topic has four topics. First, introduction. Second, experimental. And third, result and discussion. And the last, conclusion. The next, introduction. Isobutene is generally used as building block into the industry to produce a wide range of material. The co-formation mechanism and co-production catalyzation on the vanadium catalysts are of great importance as they reduce the co-formation and optimizing the DH catalyst in the future. DH of isobutene implies PT or chromium-based catalyst is widely applied in industry. However, important advancements need to occur to reduce catalyst cost and environment impact while increasing stability and activity. For the picture, the carbon effect of carbon is a three. One, chemisorb strongly. Two, totally encapsulate. And three, pack micro and mesopore, such that acid of the reactant. For the experimental, there are three topics. For the first, catalytic preparation. First, ammonium vanadium powder as precursor of vanadium oxalic acid and potassium nitride used as a support material. And then you have to dissolve in the ionized aqueous solution with more ratio 1:2. Then add pseudobromide to the solution under the stirring process. You have to the mixture was dyed in water at 70 Celsius for hours and then transfer to an oven at 120 Celsius, followed by calcination burning 550 Celsius for 10 hours. Catalyte and the next, the catalyte characterization. The sample will be treated at 300 Celsius degree for 3 hours to remove absorbed impurity. Second, the sample was oxidized from 50 to 750 Celsius degree into percent volume oxygen, and it was released in helium flow. And the last, the fixed dissolved ammonia was removed by holding the sample at the absorption temperature for 0.5 hours in the helium flow of 30 milliliters per minute. And the last topic, experimental, is catalyst evaluation in the DH of isobutene. You have to use a calculation conversion of butane and selectivity of isobutene. Result and discussion. For the first, structural characterization of DH and perform. You have to look at the fifth one, the conversion of isobutane and U of isobutane increased and
2
then
minutes left.
decreased steadily. On the other hand, the steadily decreased during the first 1.5. Nature of coke, the peak have a three peak. One peak one, you have to peak two, you have to see red and peak T. For the another literature review, the TPO is of chromium aluminum oxide react at 500, show that the coke readily oxidized with a small band appearing at 422. They show that greater amount of coke are deposited when increasing reaction temperature and change in coke structure. Acid property, the decrease of NBS is greater than that of the NLS, resulting in an increasing of the ratio with extending time on stream. For the conclusion have the three topics. One, as time increasing, coke that cover vanadium catalyst result in DH value decrease. This also result in decrease both the acid content and strain wide. NLS per NLB increase. During the DH reaction, the coke deposit on vanadium-based catalyst is in aliphatic or aromatic structure. And last, the process of making coke is complicated because many reactions occur during DH reaction, such as cracking or oligomerization and aromatization, contribute to formation of coke.
Thumbs up.
Thank you for your attention.
Okay, just in time. Thank you. Nolapan. Nolapan. Okay. Are you ready? Please share the screen. Nolapan. มีใครรู้จักเพื่อนไหมช่วยตามมาหน่อยเข้าใจเวลาผิดหรือเปล่านลพันธ์นอนนิวอะไรเนี่ยชื่อ
เขา
ถอนเหรอ
เขาออกไปแล้วครับ
อ๋อออกไปแล้วเนาะโอเค
เขาส่งอีเมลแจ้งกัน
อ๋อออกไปคือลาออกเหรอ
โดนออกเพราะว่าเกรดกับคะแนนอังกฤษส่งไม่ทันอะไร
โอเคไม่เป็นไรOkay, as we have as she has already resigned from the department, so we will skip to the next speaker. I would like to ask Namphon, are you ready? If you're ready, please share the screen and we will have some time so we can finish earlier. Okay, please start. We cannot hear you. Can you test the microphone again? There's no sound. Maybe select the correct microphone from the Zoom app. Check if you choose the right microphone. Okay, can you test the microphone again? No, we cannot hear you.
Hello.
Okay, yeah, that's it.
Hello, teacher.
Okay, let's start. Thank you.
Hi. Hello.
Yes, we can hear you now.
Okay.
Okay.
Good morning, everyone. My name is Namphun Slikun. Today, I would like to present about rhodium doping effect on coking resistance of nickel on SPA 15 catalyst in reforming of methane. Let's start with introduction. In the development of nickel-based catalyst for carbon dioxide reforming of methane or DIM, a major focus is directed on the effective suppression of carbon deposition on catalyst surface. During the reaction, it has been pointed out that the origin of carbon deposition during DIM mainly occur where it enters methane decomposition of carbon monoxide. Disproportionation. Promoter and catalyst particle size are very important in controlling carbon deposition on nickel-based catalyst. In the next part is experimental with catalyst preparation, and the sample paper were denoted following this slide, where the value is the weight ratio of rhodium nickel. Then the characterization there are 4 instruments used for analysis is TPR, XRD, TEM, and Perkin-Elmer. In the next part is result and discussion. The figure 1 for all catalysts, one mean reduction peak center at around 340 to 400 degrees Celsius is observed can be explained by the reduction of supported nickel oxide species in different interaction with the support surface, and the rhodium-free nickel on SPA 15 catalyst for a strong peak at 391 and the shoulder at 489 degrees Celsius. This means an uneven distribution of nickel oxide species interaction differently with the support. The mean peak is shifted to 369 degrees Celsius in 0.02 rhodium nickel on SPA 15, indicating that the reduction of nickel oxide is promoted in the presence of the noble metal. And the figure 2A is the small angle XRD pattern of the catalyst. There are three resolve peak of SPA 15 and index reflection associated with hexagonal symmetry in the large angle XRD pattern in the figure 2B. The reduced nickel on SPA 15 and rhodium nickel on SPA 15 sample show the refraction at this. Aside to nickel fade with the directed constant of 3.523 amstor. For the mono peak associated with rhodium was observed, suggesting that rhodium is well dispersed or the content of rhodium is too low to be detected by XRD. And the figure 3 shows the same image of the reduced nickel on SPA 15 and rhodium nickel on SPA 15 sample. It can be concluded that the presence of rhodium in nickel catalyst lead to a decrease of the nickel particle size. Additional of small amount of rhodium to monometallic nickel catalyst lead to a increase of the initial activity. The yield of hydrogen and carbon monoxide as a function of the time on steam for the first 30 hours are present in the figure 4. The figure 4 show the apparent activation was currently observed over the monometallic nickel catalyst during the 30-hour time on steam. The yield of hydrogen and carbon monoxide over nickel on SPA 15 catalyst dropped. It is important to point out that the rhodium promoted 0.02 rhodium nickel on SPA 15 catalyst is quite stable for the IM reaction. It can be observed that even adding small amount of rhodium, the stability of bimetallic rhodium nickel catalyst for the DIM is considerable improved with respect to the monometallic nickel catalyst. Next, past conclusion. The effect of rhodium on nickel SPA 15 catalyst was investigated for carbon dioxide reforming of methane. Comparative study between supported monometallic nickel and bimetallic rhodium nickel catalyst show that the high catalytic performance of rhodium promoted nickel catalyst arise from the interaction between nickel and rhodium in the bimetallic system, which provide higher metal dispersion and improve reducibility of nickel and coke resistance. There are recommendations for this work. One that in the future maybe use microporous instead of mesoporous because microporous molecular seed have excellent property by virtue of their narrow pore distribution and process good stability, high selectivity, and activity due to their crystallinity. And try out another more noble method to compare efficiency of removal for deposit carbon for improved reducibility of nickel and coke resistance. Thank you for your attention.
Okay, thank you, Namphon. Patika, please start your presentation.
Okay.
Okay, you can start now.
Teacher, can you hear me? Okay. Good evening, teacher and everyone. Today we present about the poisoning effect of PB on magnesium titanium dioxide catalyst for selective catalytic reduction of nitrogen oxide with ammonia at low temperature. SCR catalyst. We use vanadium tungsten oxide molybdenum dioxide on titanium support. It is toxicity of vanadium species, the formation of nitrogen dioxide, high temperature, high oxidation of sulfur dioxide to sulfur dioxide. The catalyst susceptible to the deactivation from high sulfur and high dust. Now we develop two manganese cerium type on titanium support with high activity and selectivity for NOx removal at low temperature. Lead poisoning. PB is one of the representative of heavy metal in the flue gas of coal-fired boiler. PB has intense toxicity to the SCR catalyst, which greatly reduce the catalytic activity. PB is the flue gas exit into form. One is particulate, two gas. Part of palladium is easily absorbed and condensed onto the surface of fine particles such as PM1 and concentrate of fine art. Other part of PB is converted to palladium, palladium oxide, palladium dioxide in the combustion reaction and enter the atmosphere. The concentration of small particles and gas PB discharged to the atmosphere was relatively high, which cannot be captured by the dust collector and may bring severe impact on the catalyst for its SCR. The figure shows the activity of the PB manganese cerium titanium dioxide catalyst with different PB loading. At a low temperature less than 150, the NOx removal rate leads to both the reaction temperature and PB content. At a higher temperature, more than 150, the doping of PB results a significant decrease in the NOx removal efficiency. The NOx removal efficiency decreased more evidently with the increase of PB content. The figure shows the NO catalytic oxidation reaction on a catalytic sample is a kinetically limited process. The figure shows the optimal structure of manganese titanium. Red is oxygen, purple is manganese, and green is PB poison. The doping of PB changes surface of titanium dioxide. PB atoms are all bound to the oxygen atom, and the bond length of palladium oxygen is 2.056 angstrom. It makes the magnesium oxygen bond extend. Oxygen vacancy harder to create. It is well recognized that oxygen vacancy is favorable to the formation of chemisorption oxygen on the catalyst surface and promote SCR reaction. The figure shows the optimized structure of NO absorption on manganese titanium. NO molecule is bound to manganese atom and palladium atom. The doping of palladium on manganese titanium catalyst would decrease its NO absorption ability, unfavorable to NO catalytic oxidation. This slide shows the characterization of the PB poison. With the increase of PB loading, the specific surface area, total pore volume, and average pore size decrease, which will be unfavorable to the absorption and mass transfer of the reaction on the catalyst surface. The figure shows the SEM image of various catalysts of phase catalysts. Manganese and cerium oxide were highly dispersed on catalyst surface. After doping with PB, more crystallization and accumulation of metal oxide appear on catalyst surface. The dispersion of the metal oxide on the catalyst surface become poor. This specific surface area of the catalyst decrease and the micropore are blocked. This slide shows the FTIR spectra of catalyst. The intensity of peak at 1401 and 1630 negative 1 centimeter decrease with
2 minutes left.
With increase of PB content indicating a decrease of the ammonia species while aspartate and luric acid, which was caused by the decrease of acid site on the catalyst surface due to the deposition of PB. A low PB loading may have a curtain promoting effect on the catalyst, but with increase of the PB loading, the poisoning effect surpasses far the promoting effect. The figure shows the ammonia TPD pattern of catalyst. The ammonia dissolution peak at the low and medium temperature did appear, indicating that PB doping greatly reduced the activity of the catalyst. PB poisoning mechanism. The PB doping has strong inhibitory effect on the absorption of ammonia at the lipid acid site and boracic acid site on the fat catalyst. The addition of PB several damage the acid site on the catalyst, and the ammonia absorption and activation function are also greatly suppressed. PB may not only reduce the absorption of ammonia species on acid site, but also reduce the type of nitrate species, therefore reducing the catalytic activity of the catalyst in SCR. The reason for the PB poisoning: 1. PB doping reduce the specific surface area and total pore volume of the catalyst and hinder the absorption and mass transfer of gas on the catalyst surface. 2. PB doping make the manganese oxide change from a high disperse or among fast form to a catalyst crystal structure. 3. PB doping can reduce the concentration of manganese and serum and change the manganese dioxide phase to trimanganese tetraoxide phase, which influence the redox cycle reaction from these. 4. PB has an obvious influence on the acid site on the surface of the catalyst, which greatly limit the absorption and activation of ammonia. Reference. Thank you for your attention.
Okay, thank you, Patika. We have 2 more speakers left, Pisit and then Victor, who has missed his presentation at 9 a.m. And referee for Mr. Victor, please be prepared for the last lecture, okay? Now, Pisit, please present your work.
โอเคครับ
ครับ
Okay, so everyone, you can see my slide and here's my white clearly or not?
Yeah, everything is all set. Thank you. Please continue.
Okay, so hello everyone. Today I would like to present the topic of sulfur poisoning of iron promoted nickel aluminum catalyst for carbon dioxide methanation. This outline of this topic I will talk today. Global warming is one of the problems that we have to concern. The increasing of carbon dioxide concentration in atmospheric pressure is one of the major causes of global warming. NOAA reported the significantly increasing of carbon dioxide concentration in air since 1960 to 2020. One approach to reduce carbon dioxide concentration is carbon dioxide methanation, which is converting carbon dioxide into the methane. Methane can use as a fuel due to its highly energy resources. In commonly, carbon dioxide methanation is heterogeneous catalyst and highly exothermal reaction. Literature review of heterogeneous catalyst. Sonia Albero et al. Said that use nickel as active metal, it will give a high selectivity on methane and also low cost. With use alumina as metal support, it will improve stability of catalyst, but it's still easy to activate by thermal. Thomas Berger et al. Found that iron promoter can enhance the catalytic activity and improve the resistance against deactivation. So iron promoted nickel catalyst is the most suitable for carbon dioxide methanation. Sulfur poisoning. Morris Group said that catalyst not only stresses by long-term deactivation, but also impurity in the feed, which is uses carbon dioxide that separate from industrial exhaust gas. It contains some sulfur, and sulfur is very quick and irreversible poison on nickel catalyst. Sulfur poisoning of ion promoted nickel aluminum catalyst. This is the data that get from Morris Book et al. Experimental of sulfur poisoning divided into the two parts. The first part is in situ sulfur poisoning. Was co-feeding of 5 ppm of hydrogen sulfide and 4 per 1 profile of hydrogen carbon dioxide and argon respectively, though the fixed bed reactor until its absence of methane, and then take the catalyst to test carbon dioxide, hydrogen adsorption, and CHNS analyzer. In the second part is ex situ sulfur poisoning was achieved by witness impregnation of ammonium sulfide on the catalyst, and then press sieve, activate aging, and then work with argon and study effect of catalytic performance dependent on temperature, and also take the catalyst to test carbon dioxide, hydrogen adsorption, and CHNS analyzer. The result and discussion of in situ sulfur poisoning on catalytic measurement of catalytic deactivation and hydrogen sulfide poisoning at 400 degrees Celsius. This figure shows carbon dioxide conversion after aging. The carbon dioxide conversion divided to three states. The state one is hydrogen sulfide is absorbed at the front end of the hotspot, causing the activation on this area. And but carbon dioxide conversion stay constant because non-poisoned fraction of the fixed bed reactor still reach equilibrium. In state 2, the poisoning zone moved to the end rear of the fixed bed, and the non-poisoning fixed bed is small, resulting carbon dioxide conversion drop very fast. And the last step is the fixed bed is saturated by sulfur, and the catalyst methanation ability is completely lost. Then one is sulfur resistant. The table 1 shows sulfur uptake of ion promoted is higher than unpromoted catalyst, and figure 2 confirm that hydrogen sulfide not only absorb on nickel catalyst but also absorb on ion promoter, resulting or in the other word you can say ion promoter can protect nickel metal from sulfur, resulting in high catalytic performance, catalytic lifetime. And about carbon dioxide adsorption, ion promoted catalyst is higher than unpromoted catalyst. About ex situ sulfur poisoning catalytic measurement, in this two graph you will see non-poisoning case event or poisoning case.
Hello. ฮัลโหลฟุก
ครับเขาน่าจะเน็ตหลุดอะอาจารย์
ใช่ไหมโอเคร
ค
อ
รับ
แป๊บหนึ่งso we wait for him ใครเป็นเพื่อนพิสิทธิ์บ้างอ่ะช่วยไลน์ไปบอกเลย so we wait for him to reconnect พิสิทธิ์เมื่อกี้หลุดอ่ะเรายังไม่ได้เปิดไมค์
Oh, hello. Sorry for my internet connection.
okay now he's reconnected
Okay, so
okay.
which part that I have to prepare last
so
time?
maybe this part resolve and discussion okay
Okay. So let's continue it. Sorry. And in this part, X2 sulfur poisoning catalytic measurement. In this figure, you will see non-poisoned case, even or poisoned case, ion promoted catalyst giving higher methane yield at the blue line, higher than methane yield of nickel catalyst unpromoted at the back line. And this table show activation energy. After poisoning, it is increased due to the sulfur atom block the active site. And from previous data, activity of ion promoted nickel catalyst is higher than unpromoted nickel catalyst. But in this table about carbon dioxide uptake of unpromoted nickel catalyst is higher than ion promoted nickel aluminum catalyst. So it can conclude that the carbon dioxide uptake cannot describe the activity of ion promoted catalyst, but the carbon dioxide uptake can describe it. So from the result, it can conclude that if we add the ion to be promoted of nickel aluminum catalyst, it will increase the activity of the catalyst and also improve the resistance of sulfur poisoning. And about future research, investigation of scalable preparation of ion promoted nickel catalyst. That I have to introduce the ion promoted nickel catalyst is most suitable for carbon dioxide methanation. So if it can scalable and if catalyst property is not changed and the term of economic is still acceptable, it is promising to use as commercial scale. So this is all of my presentation today. Thank you for your kind attention.
Thank you. The last presenter, Victor, are you ready?
Yes.
Okay.
Okay.
And referee for Victor, please prepare. I think referee number 6 and 7. So Muhammad and Gulanat. Okay, Victor, please start.
Okay. Okay, good morning, everyone. I'm going to discuss about the hydrogenation of nitrogens and catalyst deactivation using gold nanoparticles on titanium dioxide as an example case. The content table for this presentation is a general overview of the hydrogenation process, different approaches to the hydrogenation process that have been used for the last 60 years, 60, 80 years, previous ideas, the results and drawbacks, current technologies and catalyst use, the use of molecular simulations to aid catalysis, in situ techniques, photocatalysis and electrocatalysis, and some brief conclusions. First, we have to ask why hydrogenation of nitrobenzene. First, nitrobenzene is produced from the nitration of benzene, which is a highly toxic compound. And the nitrobenzene is also a highly toxic compound, and it's really readily absorbed through the skin, which is commonly found as a waste in the low concentration, but dangerous concentration in the wastewaters. And it's mostly used for aniline production. And we can see that its value is $92 per liter. But when we go to aniline, the toxicity is a little lower, but their uses are much higher. It can be used for production of urethane, dyes, and conducting polymers, and many other products. And its value is much higher, at least $200 per liter. So that's why the nitrogen hydrogenation is a relevant topic. As a general overview, the hydrogenation process, this is the accepting mechanism for hydrogenation, which here we can see that if we go only through the direct hydrogenation, we require at least 6 electrons in the most direct process, which is a really, really complicated process if we see this for these kind of molecules. And we have a wide possibility of intermediates, and all these intermediates are a function of the reaction media, a function of the catalyst we use, a function of the substrate we use, and the temperature we work in. So the selectivity of this process has been the major challenge during the last 80 years. So for the previous ideas, between around 1960s and 2000s, the focus on research was on thermal catalysis and thermal processes around 500 degrees to 600 degrees. As we saw, the boiling point of nitrobenzene is around 200 degrees, so we have to go way above that to have effective catalysis. Then we have to add hydrogen. And when we are working on thermal catalysis, we can find some good results, but the major trouble here is the deactivation of the catalyst. To study that, before the 2000s, there was a big development of empirical kinetic models. Many people use different catalysts. As an example, when using nickel, they show that there's no competition between the absorption of hydrogen and nitrobenzene. So they found two major pathways for deactivation of the catalyst. First, the poisoning. There's a strong absorption of aniline and a slow diffusion of aniline outside of the catalyst structure. Then this creates a competition for the active sites between nitrobenzene and aniline. And also, when we increase the concentration of nitrobenzene too much, the conversion decreases and we have less selectivity. Also, we can see that there's a lot of coke formation on the active side. On the left-hand side, you can see that there's the lower image is the coke formation as a function of time. We can see that there's a linear relationship between the coke and the time. That means that the coke is non-selective. We have coke in the active sites and the substrate. And the coke was also the coke formation was also a function of the flow rate as a function of the nitrogen concentration. And the most used process for regeneration of the catalyst was using hydrogen at high temperatures, but this process was really unsuccessful, reaching only like 30% of the initial activity. So with the development of new technologies, they started using like simulation, computational simulation. So in this case, we can actually see how the catalyst will behave in the presence of our substrate. In this case, we can see that on the right-hand side, you see the absorption of the nitrobenzene on titanium dioxide can go through different modes, depending if we have like oxygen vacancies or not, or we don't have oxygen vacancies.
2 minutes left.
In any way, the absorption can go through the ring or the nitro group. And when we add gold nanoparticles, the absorption with the nitro group improves the selectivity and the activity. The use of in situ techniques aid to for preaching allowed to see the intermediates in the surface of the catalyst, so we have more information. Then lately, the last years, the development of photocatalysts have led to low temperature reactions. So I mean, no coke, no need for external source of hydrogen, use of different solvents, When we have longer chain alcohols, at least like isopropanol, we have higher selectivity. We can improve the light absorption properties with nanoparticles, less byproducts or byproducts that are added value. We need the disadvantages: UV light required, lower production and thermal processes, but high selectivity, at least 99% for azoxystrobin in this case. When we go to electrocatalysis, we have also another set of advantages. The energy input is more controlled, we have higher energy efficient, and we can control the byproducts if we are within the working window. The disadvantages: lower production rate, low selectivity, high competition for the active sites, small active area, requires conductive media, and poisoning. And the selectivity is much lower, 30% around, and a conversion of 80%. So as a conclusion, in thermal process, we have poisoning on coke formation as main passivating mechanism. We can use the computational simulation to help promote passivation and to help avoid passivation by providing information, the use of in situ techniques to see the different intermediates. Photocatalysis and electrocatalysis are the new trends and the future research fields, but still have a lot of challenges. And the good thing is we have no coke formation in these conditions. So thank you.
Okay, thank you, Victor. And thank you everyone for joining us for this week. And don't forget 3 things to send your presentation in PDF, and then your report, which is set to be on the deadline is, I think I changed to the 7th of May, so next 2 Fridays. And the last thing is the evaluation form. Okay, and if you would like to attend your friend's presentation next week, you can join. If not, you can leave and send all the works, and yeah, we will see you after the grade comes out. Okay, and thank you everyone. Okay, class is already done. Okay, you can all leave now. Class is
Yes, thank you so much, Professor.
Thank you everyone. Thank you.
Thank you, teacher.
Thank you. And I will upload the file today, this video. Thank you.